Welcome to section 5.4, the fundamental theorem of calculus. So, there's something about this statement that should ring with you. And it should be this word right here. The fact that this is the fundamental theorem of calculus should tell you that this has something about it that is incredibly important, a very, very important concept for calculus. Right? And in this section, we have several objectives we're going to take a look at. We are going to use the definite integral with the fundamental theorem of calculus. We're going to take a look at something called the mean value theorem. We're going to take a look at average values. We're going to take a look at the second, not the first, but the second fundamental theorem of calculus. And then we're going to take a look at something called the net change theorem. Now, in my opinion, this one right here is one of the most important ones in terms of application of calculus. Right? In terms of the word problems or the application problems, the net change theorem is really, really important. All right, but to get started, first thing we're going to take a look at is the fundamental theorem of calculus. You know this is going to be good because it has fun right in the name. All right, the fundamental theorem of calculus. I love that joke. It's absolutely terrible, but I love it. All right, so the fundamental theorem of calculus says that if you have a function f, little f, and it is a continuous on a closed interval function. That means draw without your picking your pencil up. And you have another function, big F, and big F is an antiderivative of little f. Remember, an antiderivative on that same interval AB. Then the following is true. That is, the definite integral from a to b of little f can be found by taking big F at b and subtracting off big F at a. So basically what this tells us is we no longer have to do those silly summations. We no longer have to work at taking and finding a summation as I goes from 1 to n, and then taking the limit as that n approaches infinity for some f of c sub I times delta x to find this definite integral that we can just take and find an antiderivative and make it work that way. So if we were to think about some of the problems that we've done so far, and if we were to think about what we had to do to make them work, right, we can now do them much more quickly. So I seem to remember from last section we had a problem that looked like this. Where our job was to find the value of the definite integral from 0 to 1 of x squared plus 1 dx. The parabola shifted up 1. Now, when we did this last time, what we had to do is we had to find a summation limit. But this time all I have to do is just say, okay, well that's going to stand for the little f in this definition. Tell me what big F is. Well, big F is going to be 1/3 x cubed plus x. And then this is now going to be the big F in this definition. And then I'm going to use some notation here. Some notation we have not seen before, so I'm going to change color. And I'm going to evaluate that from 0 to 1. Now this vertical line here means to take the function that is represented to the left and evaluate it at the upper limit and then the lower limit and subtract. It's the notation that tells us to do that. Right? Now, wouldn't that be so much easier than what we had to do before? All that summation business. Okay? All right, so basically what was happening is two guys were working on it. Newton and Leibniz were working on derivatives and integrals. Newton was working on integrals, Leibniz was working on differentiation, or vice versa. I can't remember which one was doing which. And they actually found that these two things came together in the middle, and that there was a relationship between antiderivatives and derivatives and integrals and all of that business. Okay? Now, I want to point out something, and this is an incredibly important box right here. Okay? And it talks about the difference, or it relates or brings it to light the difference between anti-differentiation, that is just finding an antiderivative, and evaluating a definite integral. Right? So throughout this chapter, we've been using a symbol, this integral symbol here. And we've been using it in two different ways because we've modified it slightly when we wanted to represent a definite integral, and we've neglected that modification when we wanted it to represent an antiderivative. Right? On the left over here, you'll see that our integral symbol is lacking those limits of integration, which means that in this situation, we simply wanted to find an antiderivative. Over here, we have limits of integration, which means that in this situation, we don't want it to find an antiderivative. We want it to find the value of a definite integral. Right? Now, whether that definite integral represents area or whether that definite integral represents something else, it just depends on how the function f of x looks. So what we need to do is we need to become very, very good at looking at a problem and determining whether it's just a simple anti-differentiation problem, like the one on the left here, or whether it's a true definite integral problem like the one on the right. And basically what it boils down to is how do we want this to work? Do we want this to be an anti-differentiation problem? Because if it's an anti-differentiation problem, I don't put limits. Or is it a definite integration problem where I do put limits? So it's a subtle difference, but it's a huge difference in what the answer is. So we need to make sure that we're eyeballing that, making sure we're taking a good hard look at it. All right, so let's take a look at the guidelines for using the fundamental theorem of calculus. Okay. Step one is make sure that you can find the antiderivative of your little f. If you can find the antiderivative, then you can use the fundamental theorem. If you cannot find it, then you have to go back and use limits of a sum. Now, this is not a new idea. Remember way, way back, think way, way back, all the way back to, it would have been, what? September? August? No. Way back, like the first part of the book. Way back when we did derivatives for the first time. Right? And we started applying all those rules for taking a derivative. We said, hey, if you can't do this, if you cannot find a derivative of a function, then what you must do is you must take that limit business. Right? So do you remember this? F prime of x was equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And we said that you had to use this definition if you couldn't find a derivative using one of the shortcuts that we came up with. Same thing is going to be true here. You're going to have to use the summation if you can't find an antiderivative. I don't think there's a single problem in here that we're going to have where you can't find an antiderivative if you remember your derivative rules well enough. But in the big picture of things, there are things out there that don't have antiderivatives, and if they don't have antiderivatives, you have to use the limit of the sum, and the limit of the sum can be brutal. Okay, so step one is done. We found an antiderivative. Let's just assume that for whatever function we're working with, we found one. Now we need to do this. My job is to take the definite integral of a little function f of x starting at a, stopping at b. I'm going to do that by first finding an antiderivative and then evaluating that antiderivative at the upper limit of integration, that's the b, and then evaluating that antiderivative at the lower limit of integration, that's f of a, and then finding the difference between those two. Subtract f of a from f of b. Okay? Now, one thing that is interesting is the notation that this author chooses to use right here. Right? Now, almost every other book I've ever seen would have written that step like this. But for whatever reason, this author chooses to put these little tails on this. I've not seen that elsewhere. So what I'm attempting to tell you here is If I haven't seen it elsewhere, you're probably not going to see it elsewhere. So you're most likely going to see it written like this everywhere, not like this. Okay, this seems to be unique to Larson. Now, why they chose that, I don't know. But just so you know, the two things mean the same thing. They mean find an antiderivative, evaluated B, evaluated A, and then find the difference. Okay? So for example, here I have a definite integral. My little function f of x is x cubed. I have lower limit of integration, upper limit of integration of 1 and 3. Right? What's this? Well, that is, in terms of the language of integration, that's the f of x. That is an antiderivative. Now you might be asking yourself, where's the plus c? Well, honestly, we don't need it. That's covered down here in step 3. Because imagine that c was there. So imagine that you found it, and there's the c, right? Why am I using the arrow? I don't know. Let's get rid of it. Imagine that you found the plus c. Well, there's the f of b, the upper limit. There's the f of a, the lower limit. But what's going to happen to those two c's? Well, when we distribute the negative in there, the c's are going to cancel. And since that will always happen, since the c will always cancel, always going to cancel, why should I ever write it? Right? Which is why here you don't see the c written. Anyway, okay, so then what's this mess? Well, that's upper limit of integration. That's lower limit of integration. And so we evaluate the function at the upper limit of integration. We evaluate the function at the lower limit of integration. And then we subtract to find the difference. Okay? And then everything to the right of that over here, that's just the math that's involved. And so 81/4 minus 1/4 is 84. 84 is 20. And we found the value of the definite integral. Now, given that our cubic function is entirely positive on the interval 1 to 3, you could make the argument that that 20 represents the area bounded by that curve. Or you could just say the value of the definite integral is 20. All right, so let's do an example. All right, so I want to evaluate the definite integral from 1 to 2 for the function x squared minus 3. So in terms of the definition, that's our little f. So the first thing I need to do is I need to find big F. Well, the antiderivative of x squared would be 1/3 x cubed. The antiderivative of 3 would be 3x. And then I need to evaluate this from 1 to 2. Okay, so now I'll evaluate it at 2. That's going to be 1/3 times 2 cubed minus 3 times 2 minus, I'll evaluate it at 1. 1/3 times 1 cubed minus 3 times 1. Okay, this is what going to be 8/3 minus 6 minus 1/3 plus 3. Let's see, I've got 7/3 minus 3, so that's negative 2/3 when it's all said and done. So the value of the definite integral from 1 to 2 of x squared minus 3 is negative 2/3. Now, the fact that the value of the definite integral is negative should tell us something about this function. It should tell us that the function is, there's more of the function below the x-axis than there is above the x-axis on the interval from, what is that going to be, 1 to 2, or that the value of the definite integral is negative 2/3. All right, one more, and then we'll call this video. I need to find the value of the definite integral from 1 to 3 of x cubed. All right, so lower limit of integration 1, upper limit of integration 3, function of integration x cubed. Step 1, find that antiderivative. The antiderivative of x cubed is going to be 1/4 x to the 4th And then I need to evaluate that from 1 to 3. So that's going to be 1/4 times 3 to the 4th minus 1/4 times 1 to the 4th. Okay? 3 to the 4th is 81, so I have 81/4 minus 1/4, which is 80/4, or 20. Now I just realized something. Isn't that this? Didn't I just redo the problem we just did up there? All right, I'm going to need to fix that. Error number 58 for today that I need to change. All right, and that's going to bring us to the end of video 1. We'll come back in video 2 and just keep doing more and more and more examples. All right.